Welcome back to another lesson in MCR3U. Today we'll be looking at domain and range, and we'll also look a little bit at inverse functions in this lesson as well. So when we look at the term domain and range, we covered this a little bit in the last lesson, but domain, again, to repeat that, is a set of first coordinates, which are usually x, of the ordered pairs in the relation. And the range is a set of second coordinates, usually y, of the ordered pairs in a relation. And so the domain of a relation is the set of values of x in the relation. The range of a relation is the set of values of y in the relation. Again, the domain and range of a relation are often described using one or two ways, either set notation or interval notation. Here, if we look at this first example, this is determine the domain and range of each of the following functions. And so here, what I just want to review quickly is, again, if it's a dot like this, which is what is we call closed circle, again, that means that it includes the point. If we draw a circle that's open, which is called an open circle, that means that it does not include the point. Okay, so if we look at this here, so we have a line, and it starts at -1 and -3, and then it goes, and it continues on, and it can be infinite x values in the positive direction. So here for writing it in set notation, so here we'll write a capital D to represent the domain, and here we want to see, again, a few things. So remember, if we're looking at some signs as well, so just repeat this here. So this sign means that it's greater than. This sign means less than. And remember, if it has the line below, it means that it includes the value. So here we see that our domain, again, x has to be greater than or equal. So here we'll use the greater than or equal to -1. Here we're also indicating x has to be greater than or equal to -1, but after that restriction, x is an element of any real number. And so it can be any real number from -1 to positive infinity. We look at our range here, so indicate that by an R. And so let's see what our Y values are. Our Y values here have to be greater than equal than -3. But after that restriction, Y is an element of real numbers. So again, it's not always going to be an element of real numbers. Let's just say that it's a scatter plot, for example. It wouldn't be an element of real numbers because there would be dots. So let's say instead of this being a line here, there's just dots here that it increases by. And it wasn't connected to each other. We might not say that it's an element of real numbers. We just might say that it's an element of natural numbers, of integers, so on and so forth. So although a lot of the times when we look at these functions, they are element of real numbers, it's not always the case, just to keep that in mind. Here, if we look at interval notation, so there's a couple of key things to look at when we look at interval notation. Here, if we're looking at square brackets means it includes the value. So that means it includes the value. And open brackets would mean that it does not include the value. And so here, if we're looking at interval notation, so here, again, our domain, so we're writing it in interval notation, we will write this is an element, and where does it go from? Where's the interval that it starts from? So it starts at -1 and it includes the point -1. And where does it finish? So it goes all the way to positive infinity. For negative and positive infinity, we put the open bracket because there's not a specific point in where infinity or negative infinity stops. If we look at the range here, where's the interval for y? Well, it starts at -3, and it also goes to positive infinity. And generally, the standard form is to start from like, the smaller to get to the larger. So from -1 to infinity, -3 to infinity, instead of going from infinity to -1. So from left to right, a lot of the times we'll look at it. Let's look at this other one. So here we have a parabola. In terms of the domain, x values are everything. So here for the domain for set notation, again, x is just an element of real numbers. For our range, y has to be less than or equal to 1, and then y is an element of real numbers. If we write it in interval notation, do that, it goes from negative infinity, the x values from negative infinity to positive infinity. And for our range, here it starts, here it goes negative infinity, and it stops at 1, but it includes 1. Let's look at this next graph here. Here, if we look at this, again, set notation. So the domain, again, is x is an element of real numbers. So there's no point where it stops. It goes from negative infinity to positive infinity. And our range, and it's between, so it doesn't quite touch 0, but it's between 0 and 2. So close to 0, but doesn't touch 0 to 2. So 0, the y is greater than 0, but not 0. And it's also less than or equal to 2. And y is an element of real numbers. Here, for our domain, we're writing an interval notation. Goes from negative infinity to positive infinity. And for our range, again, it goes from 0, not including, to 2, including, which means that we get the square bracket there. And lastly, looking at this problem again, opening up this time though. Here we have a domain. X is an element of real numbers again. Our range in this situation, y has to be greater or equal than -1. Y is an element of real numbers. Domain and interval notation from negative infinity to positive infinity. And our range here. Again, goes from -1 to positive infinity. Okay, so let's look at inverse functions as well here a little bit, and also apply our understanding of domain and range. So the inverse of a relation, f of x, is the relation f inverse of x, in which all of the ordered pairs f of x have been reversed. So if a point AB is found on f of x, then point BA can be found on the inverse. Graphically, this would show as a reflection in the line y is equal to x. And so the line y is equal to x, so I just show this on this graph, would look like this. And so if you put your function on here, then found the inverse, it will reflect across this line. So again, here, this f, the -1x, is read as f inverse and not -1, and -1 is not an exponent. This is the notation to represent an inverse, but here the inverse f -1x is not equal to 1 over f of x. The inverse of a function may or may not be a function. If the inverse is a function and the original function is f of x, again, then the inverse is called f -1 of x. So a couple of methods of determining the inverse function is dependent on the information given. So if we're given the table values or ordered pairs, what we do here is we switch the xy from f of x to yx for the inverse. If we're given the equation, we switch the x and y and we solve for y. And then here, if the inverse is a function, put it back into function notation as f -1 of x. And finally, if we have a graph, we can reflect the points in the line y is equal to x. So here it says determine the inverse of f of x is equal to 0, 3, 1, 3, 2, 3, so on and so forth. So here, when we look at our inverse, so our inverse here, so we're going to just replace the a with the b and the b with the a. So here we would have our order pairs of 3, 0, 3, 1, 3, 2, 3, 3, 3, 4, and 3, 5. And so here is the inverse a function. So we see that the inverse is not a function. The reason, again, that we learned before in terms of function versus relation, for every x value, there are multiple y values. So for example, for 3, there's 3, 0, 3, 1, 3, 2, 3, 3, so on and so forth. And so here, let's take the domain and range. And so here, again, we have ordered pairs. So the domain here is just, so the domain range of the f of x, so the domain is 0, 1, 2, 3, 4, 5. And the range here for f of x is just 3. And the domain of the inverse, what you'll notice is it's actually the opposite, or it's flipped. So here the domain is 3, and the range is 0, 1, 2, 3, 4, and 5. And so here what we notice is that the domain and range flip. So here the domain and range flip. So here we see that the f of x domain is equal to the inverse's range and vice versa. Okay, so let's look at this here now. So it says sketch the inverse of the given function is the inverse of f of x and functions. Explain, state the domain and range of f of x. So remember, this graph, and if I draw this line, will reflect across y is equal to x. Probably the easiest thing to do here is to look at the points and then switch them. So here, this would be -6 and 1. This here would be -4 and 4. This would be -1 and 4. This would be 1 and 2. And this last point here would be 4 and 2. And so what we'll do here is we'll just flip it. So -1 and 6 now will be 1 and -6. -4 and 4 now be 4 and -4. -1 and 4 will be 4 and -1. And then 1 and 2 will now be 2 and 1. And 4 and 2 will now be 2 and 4. So if we connect these dots together, it'll look like this. And what we notice here is that, again, it does reflect across the line y is equal to x. However, here, if we hit our vertical line test, you see that here it fails the vertical line test, which means that the inverse is not a function. Inverse, not a function, fails vertical line test. Okay, so let's look at the domain and range of here of f of x. So the domain of f of x here again starts at -6, -4, -1, 1, and 4. And here the range for f of x is 1, 4, or let's 1, 2, and 4. Okay, so example 3, it says determine the equation of the inverse for the function f of x is equal to 3x plus 2. So here, if our original function is y is equal to 3x plus 2, if we reverse it, again, now it'll be x is equal to 3y plus 2, and we want to solve for y. So we'll isolate here, and so we'll have x minus 2 is equal to 3y. And so here, y is equal to x over 3 minus 2 over 3, which is our equation. Here, see that we know that our y-intercept is at -2 over 3 right here. And so we can just draw a line approximately here that will determine the function of the inverse. And the inverse here is a function. And we know that because one value, so one x value, so let's say each x value has one value. And let's state the domain and range of f of x and the inverse. And so for f of x, the domain here, x is an element of real numbers, and the range, x is an element of real numbers. And so that would be the same for the inverse. Okay. And then the last one here, it says domain, determine the inverse of f of x is equal to x plus 2 squared. And so here, y is equal to x plus 2 squared. So here we can change it. It will be x is equal to y plus 2 squared. What we want to do here, we want to square root both sides, get rid of this square. Square root x is equal to y plus 2. So here, because we square root both sides, again, when we're solving for something, we have to consider to have the plus or minus. And so here, y is equal to plus or minus square root x minus 2. So here is the inverse of function. Here, it is not a function because if, for example, we sub x is equal to 9 into the equation, y is equal to plus or minus square root 9 minus 2. Again, for each x value, we see here that there is multiple y values. So when x is equal to 9, it can be either equal to 1 or negative 5. So here, multiple y values, or multiple y values for 1. So here, then we're going to state the domain and range of f of x and its inverse. So here, if we look at this, if we have x plus 2 squared, again, if we look at that, again, x plus 2 squared, we see that x is an element of real numbers, so domain for f of x. So x is an element, so domain, x is an element of real numbers, and for our y, our range, again, y has to be greater or equal to 0, and y is an element of real numbers. So here, in terms of our inverse, I'm gonna flip that. So our domain x is greater than or equal to 0. X is an element of real numbers, and our range y is an element of real numbers.